Hello everyone, I'm Roberto Forgione, a PhD student at University of Illinois, Urbana-Champaign. I'm going to present the work I've done along with Professor Gardoni and Professor Lee from Zhejiang University, entitled Failure Probability Estimation in Reliability Analysis Using Path Sampling. This work was also presented at the EMI PMC conference in Chicago in May 2024. The primary objective of reliability analysis is to compute the probability of rare events, including structural system failures. First and second order reliability methods are generally efficient in computing the failure probability. However, they may not be suitable for complex geometries or failure domains, such as those with highly nonlinear boundaries or multiple design points, where they can either become infeasible or produce significant errors. Monte Carlo simulation can successfully handle any failure domain geometry. However, its slow convergence rate makes it computationally impractical for large-scale applications. Importance sampling accelerates the Monte Carlo simulation while maintaining its adaptability to different geometries. However, the effectiveness of importance sampling relies heavily on the selection of an appropriate sampling density. In this presentation, we propose a method to estimate the failure probability based on path sampling. We use a parametric IS density that smoothly transitions from the standard normal probability density function to the optimal IS density as its parameter z decreases. We introduce two estimators for the failure probability. The first estimator leverages the principles of thermodynamic integration, reducing the failure probability to a one-dimensional integral solved by quadrature rule. The second estimator is based on stepping stone sampling, computing the failure probability as the product of the ratios of normalizing factors of adjacent IS densities. We introduce a criterion that assures a smooth transition from the standard normal PDF to the optimal IS densities. By approximating the Kullback-Leibler divergence, we adaptively select the values of the parameter z. We reduce the discretization error by ensuring we maintain a small KL divergence between consecutive IS densities. Then we test our method with 3 benchmark problems and compare the results with other IS methods available in the literature. Importance sampling is a popular variance reduction technique designed to accelerate the standard Monte Carlo simulation. Its basic principle is to define a biased sampling distribution that targets the failure domain more frequently compared to the standard Monte Carlo simulation. IS samples from this new importance sampling density instead of the original probability density. The success of the IS technique depends on the choice of the IS density. Given an estimator to evaluate the failure probability, we can find the optimal IS density by minimizing its variance. However, we cannot directly sample from the optimal IS density, as it depends on the unknown failure probability. Several techniques can be used to approximate the optimal IS density. Density approximation methods directly approximate the importance sampling density by using a member of a family of parametric or non-parametric probability density functions. Parametric methods define a finite mixture model, which is a convex combination of PDFs of the same type that depend on a vector of parameters theta. A popular mixture model is the Gaussian mixture. Non-parametric methods such as kernel density provide an estimate of the IS density based on a finite set of data points, without assuming any specific parametric form for the distribution. Both parametric and non-parametric methods aim to approximate the optimal IS density by minimizing a discrepancy measure, for example the mean squared error, between the optimal IS density and the chosen family of approximating densities. Limit state function approximation methods consist in replacing the computationally demanding limit state function with a fast-to-evaluate surrogate. In doing so, we redefine the IS density, as it is proportional to the approximated failure domain. An example is the Gaussian process, which assumes that the actual limit state function is a realization of an underlying Gaussian process. In the proposed path sampling method, we consider a parametric highest density for estimating the failure probability. The parametric highest density has Z as parameter that varies from 1 to the positive size of 0, or alternatively 0 plus. For Z equals 1, the normalizing factor is equal to 1/2, and the parametric highest density returns the standard normal distribution. For Z that approaches 0 plus, the normalizing factor is equal to the failure probability, and the parametric highest density returns the optimal highest density. For Z instead between 1 and 0 plus, the highest density is a transition between the standard normal PDF and the optimal highest density. Using a decreasing sequence of parameters Z from 1 to 0 plus, we create a continuous path between the standard normal PDF and the optimal highest density, which explain path sampling. In order to effectively propagate the samples through the path, the step size between two consecutive parameters Z sub k and Z sub k minus 1 must be small, which requires a large number of highest densities. This idea is also used in annealed importance sampling, where the aim is to find a sequence of intermediate distributions that smoothly transition from a simple distribution to the complex target distribution in Bayesian inference. The first estimator of the failure probability is defined following the principle of thermodynamic integration. Such method is based on the fact that the logarithm of the failure probability can be represented as a one-dimensional integral. This is possible because we know the values of the normalizing factor at the extreme values of the parameter Z, 1 and 0 plus. Using a decreasing sequence of the parameter Z, the one-dimensional integration can be approximated with quadrature rules. The TI estimator is based on the trapezoidal rule. Although the TI estimator is subject to both discretization error and statistical error, it can be shown that it is unbiased and consistent if the step size of parameters Z sub k and Z sub k minus 1 is sufficiently small and the number of samples is large enough. The term f hat of Z sub k is an MC estimator of the function f of x and z based on samples from the highest density. The second estimator of failure probability we propose is based on stepping stone sampling. Such method proceeds in largely the same way as the thermodynamic integration. The only difference between the methods is the formula used to compute the failure probability. This time, the failure probability is computed as the product of the ratios of normalizing factors of two adjacent highest densities. A similar idea to evaluate the failure probability has been proposed in sequential importance sampling and in subset simulation. Using a decreasing sequence of parameter Z, an estimator of the failure probability can be introduced. Such estimator is unbiased and consistent if the step size of parameter Z sub k and Z sub k minus 1 is sufficiently small and the number of samples is large enough. To ensure a smooth transition from the standard normal PDF to the optimal highest density, we use the Kullback-Leibler divergence. In our case, the KL divergence measures the difference between two consecutive parametric highest densities. Such KL divergence can be approximated using the Taylor expansion. This gives the guideline in adaptively choosing the values of the parameter Z. Starting with Z sub 0 equals 1 and given Z sub k minus 1, we propose to adaptively choose Z sub k such that the KL divergence equals a small constant C sub KL. This way we also reduce the discretization error. To estimate the KL divergence, it is necessary to have the sample x sub 1, x sub 2, up to x sub n of s from the highest density related to the parameter Z sub k minus 1. To determine a proper constant C sub KL, we evaluate the extreme case of the KL divergence between the optimal highest density and the standard normal PDF. In this case, the KL divergence is equal to the negative logarithm of the failure probability. Since the failure probability typically lies within the range 10 to the minus 7 and 10 to the minus 3, the KL divergence between the extreme values of z ranges between 6 and 16. Due to the triangular inequality, the sum of the KL divergences between adjacent highest densities over the entire sequence of parameters z sub k provides an upper bound for the KL divergence between the optimal highest density and the standard normal PDF. Setting the constant c sub kl equals to 5 times 10 to the minus 3 generally assures the best trade-off between result accuracy and computational demand. For all the steps, we keep monitoring the KL divergence between the optimal highest density and the current highest density. If such quantity is smaller than the constant c sub kl, the current highest density is set as the optimal highest density, and the algorithm stops. To illustrate the proposed method, we consider a component reliability problem as the first benchmark problem. The component has two design points, and the limit state function is a parabola with independent standard Gaussian random variables. In this benchmark problem, we use 40 initial sample points that propagate through the several highest densities by Markov chain Monte Carlo, and we set a constant for the KL divergence equals to 5 times 10 to the minus 3. Several sample sizes and constant c sub kl were used. The choice of such parameters depends on the desired trade-off between accuracy and the number of limit state function calls. The objective is to minimize the number of limit state function calls while maintaining high accuracy. And we can also see that the optimal highest density and the highest density we obtain through path sampling are similar. We can then compare the proposed method with other IS methods in terms of computational cost and estimation accuracy. The results we consider for the several benchmark problems are from the paper by Tabande, Gia, and Gardoni. The MC simulation in this case estimates the failure probability as 3.02 times 10 to the minus 3 with a coefficient of variation of 0.05. The accuracy of the proposed method estimating the failure probability is comparable to the Gaussian process method and better than the other IS method considered. The proposed method requires fewer limit state function calls than the Gaussian mixture and kernel density methods, but more than the Gaussian process method. The second benchmark problem we consider is a series system with two components. The limit state function of the system is given by the minimum of G1 and G2, where G1 and G2 are the limit state functions of the two components, and x1 and x2 are independent standard Gaussian random variables. The limit state function G1 has a single design point, while the limit state function G2 has two design points. In this case, we use 90 initial sample points that propagate through the several highest densities by MCMC, and we set a constant for the KL divergence equal to 5 times 10 to the minus 3. The constant C sub KL remains unchanged compared to the first benchmark problem, but the number of initial sample points is higher than in the previous case due to the smaller failure probability, in order to maintain the same level of accuracy. As in the first benchmark problem, we compare the performances of the proposed method with other IS methods in terms of their computational cost and estimation accuracy. The Monte Carlo method estimates the failure probability as 8.7 times 10 to the minus 5 with a coefficient of variation of 0.05. Again, we can see that the accuracy of the proposed method in estimating the failure probability is better than all the IS methods considered. And the proposed method requires fewer limit state function calls than the Gaussian mixture and kernel density methods, but more than the Gaussian process method. The proposed path sampling method is tested on another benchmark problem, and the results are summarized in the following table. We find that path sampling proves to be reliable also for high-dimensional linear problems. At the moment, we are testing our method on a component problem with a high-dimensional nonlinear limit state function. The following are the concluding remarks of this presentation. Basing on path sampling, we have defined a parametric highest density that approaches the optimal highest density as its parameter z goes to 0+. We developed two failure probability estimators based on thermodynamic integration and stepping stone sampling. We provided a criterion that assures a smooth transition from the standard normal PDF to the optimal highest density. The results from the numerical examples suggest that both the TI and SS estimator effectively determine the failure probability, while the computational demand of path sampling is less than that of other methods available in the literature. Our future work will focus on validating our method for more complex benchmark problems and real examples to further confirm the proposed method's reliability. Thank you for your attention, and if you are interested in the topics of reliability risk assessment, don't hesitate to check out the YouTube channel and the X account of the MEE Center. You can find the links in the description.